So we'll be looking at the members. You know, this is a member here, this front leg, and then this is the back leg, and then this is the seat. And the other assumption besides these all being pins, we're going to assume that this seat is level. So if we actually look at these two dots, they're not quite level. We're going to assume that they are and that the seat's perfectly level. When we come down here and look at the scissors jack, these are all pins right here. So, and we're going to be looking at this member, this member, this member, and this member in our evaluation of the loads on this thing. So I want to kind of walk through some of the stuff in the Canvas page.
Rob, you want to manually mute all real quick?
Was there a question? I couldn't quite hear that.
Would you manually mute all?
Is that manually use? I'm sorry, I still can't hear you very well.
Mute. Will you mute everybody?
Yes, I can do that. So this is our chair from last time, had me sitting in it. And we had the reaction at this front leg, and we knew my weight. And you guys had to figure out where my center of gravity was relative to the front leg, and also figure out the reaction of the back leg. This is a scissors jack, and I just sort of showed how to use that just now. We'll do it again, you can always look at it. So both of these common items are made up of 2 or 3/4 members. All of the members in the chair are 3/4 members. We have a force at the bottom, we have a force at a pin, and a pin along the front leg. And again, in the back leg, it's a pin in the leg, the contact at the ground. And then the seat has the 2 pins in the horizontal, then of course my force of sitting on the chair.
Are we going to treat the chair kind of like are we going to basically pretend it's 2D, or are we going to treat it as a 3D?
We're going to pretend it's 2D, and the same with the scissors jack.
Yeah, I noticed the chair in the Canvas module, it's such a completely different design.
So yes, we'll get to that. Yes, and it's partly because I have a lovely diagram of that, but also because it's a little simplified. People get, if I go back to the other chair, if I go back to this chair, people get hung up on the fact that the pin is here, just a little behind rather than in line. And it really doesn't make any difference, but people get hung up on it. Also the fact that this is at a slight angle is going to make it really hard to solve. So having a horizontal seat, having the pin in line reduces a lot of questions and a lot of difficulty. So that's why it's somewhat different than what's in Canvas.
Well, and the location of the slot.
Location of what?
The slot. I mean, I think we're not considering the slot, but on the Canvas module, the slot is on the back of the chair, above the, it's up at the top.
I'm not sure I understand yet, but when we get to the picture of the chair, you can point it out to me. So I just wanted to kind of review real quickly 2 force members. 2 force member doesn't necessarily have to be like a link, much like in our scissors jack. But this is what a 2 force member is it means that there's 2 forces, and of course, if you only have 2 forces, they have to be in line with each other. They have to be on the same line of action. We'll watch a little video that explains that a little bit more in detail. But most important is that a two-force member does not have to be a link. It could be, this L-shaped or this hook shape, so long as there's only two forces acting on the member, it's a two-force member. A three-force member, ironically, has three forces on it. There's only two ways that forces can act on a three-force member, and they either have to be concurrent, i.e. they all have to intersect at a single point somewhere. Doesn't always necessarily have to be on the body. It could be outside the body. But in this case, they've gone inside the body. Or all the forces have to be parallel. In our chair last week, when we looked at the body of the chair and me, we did a three-force parallel because all of them were vertical. But when we start to look at the forces in the members, we'll discover that we're really looking at something here on the left, not necessarily something on the right. So this kind of summarizes what you end up doing. So people would say, well, I may have multiple forces on my two-force link, but they're all acting at one point, and again, another point, and the resultant will always end up being such that they're in a line of action with each other, that is shown here in this two-point axial member. Here's a three-force, and then you can see how things are different. You can have forces acting at three different spots, and you can have resultants and components at each one that's somewhat different. Now, I'm going to stop sharing for a second and then reshare. Hopefully this works. Last time somebody said I could do this, and we'll try it. Are you able to hear anything there?
In this video, we will learn about two-force and three-force members. The reason why we want to learn about them is because if we can identify them in the structure, it could help us simplify the problem and make the calculation easier. Let's look at this member, and it is given that forces are only applied on 2 points on this member, say point A and point B. At first, we don't know what directions these forces are in, so let's draw them in arbitrary directions. But we know that 2 points define a line, and we can always draw a straight line connecting point A and point B. And since we can also choose to set up the coordinate system as we want, why don't we set it up this way, with x-axis along this line and y-axis perpendicular to this line. And we know that any arbitrary force in this plane can be resolved into an x-component force and a y-component force. Now let's try to write the equilibrium equations. First, the resultant moment about point A equals to 0. And since force By is the only force that could possibly create a moment about point A, because the other three forces all have lines of action passing through point A, therefore force By must be 0. Similarly, by summarizing moment about point B, we can conclude that force Ay also must be 0. And lastly, by summarizing the force along the x-axis, we can tell Ax plus Bx equals to 0, therefore Ax equals to negative Bx. So, if a member only has forces acting on 2 points, it is called a two-force member, and the two forces will have the same magnitude, opposite direction, and same line of action, which is simply the line connecting the 2 points. Similarly, if a member only has forces acting on 3 points, it is known as a three-force member, and for a 2D problem, these 3 forces are either concurrent or parallel to each other. The reason is because, let's say, 2 of the forces are not parallel, then they must intercept at a point, say point O. And since we can write a moment equilibrium equation about any arbitrary point, let's write the resultant moment about point O, that the resultant moment is 0. Since the third force is the only force that can possibly create moment about point O, because the other 2 forces have lines of action passing through point O, but it also must create a moment of 0, therefore for that to happen, it must also pass point O. I will leave it to you to prove that if two forces are parallel to each other, then the third force must also be parallel to them, following again the same moment equilibrium requirement. You should see that these conclusions on the force requirements for two force members or three force members are all derived from rigid body equilibrium equations. They are not additional conditions that we can use on top of equilibrium conditions. They simply provide alternative analyzing method that could hopefully help us simplify the calculation. Let's look at this example. We need to find the support reactions at pins A and B. If we want to treat this assembly as one system and draw only one free body diagram, then since we know that there are two force reactions associated with each pin support, together we will have 4 unknowns, but we can only write 3 independent equations, and that won't be enough to solve for all unknowns. But we can solve this problem by analyzing each member separately. Then the forces at joint C, which are internal, now become external and must be included in the 2 separate free body diagrams. But notice how they are actions and reactions. So we have 2 free body diagrams. Therefore, we can write 6 equilibrium equations in total, and that will enable us to solve for all of our 6 unknowns, AX, AY, BX, BY, CX, and CY. However, if we could realize that member AC is actually a 2-force member, since it is only subjected to forces at 2 points A and C, therefore the forces acting on it must be along this line that connects these 2 points. Now, we no longer have 2 unknowns at pin support A, since we can determine the direction of the force. Now, we can again treat the assembly as one system. Even more, we notice that member BC is also a 3-force member, and we know the direction of 2 forces acting on it already. Therefore, the third force must be concurrent with the other 2. And therefore, we can also determine the direction of the force acting at pin support B. Let's look at this triangle. If we examine the geometry, this is what we know. And then we can apply law of cosines first to solve for this side to be 1.58 meter. And then we can apply law of sines to solve for this angle to be 18.4 degree. Therefore, this angle is 71.6 degree. Now we have a free body diagram with 2 unknowns. We can write 2 equilibrium equations to solve for both of them. Negative sign in force FB indicates that its direction is opposite to what we assume. Hopefully, you've learned from this example that by identifying 2-force and 3-force members, we can effectively simplify our calculation.
All right. I just wanted to show that's I think it's a really good video. She does a great job of explaining the difference between a 2-force and a 3-force member, and why they're good. I did want to now go on to looking at exactly what our assignment is today. And let me go there. I'm having a hard time finding it. Hold on a second. Where are we? All right. So in this one, I think, Jason, you were saying that this looks different than the one that we've got. And of course, you're right, it is a little different. You can see that the slide is at the top rather than along this leg here, the back leg. But in essence, the geometry is kind of the same. The biggest difference, like I said, is the fact that this is horizontal. Last week, you guys solved for A, and you also solved for the reaction at B. You were given the reaction at A. So this week, what I want you to do is to solve for all the forces in all of the members. So that is 3 members are, again, are the front leg. So you'd be looking for the forces at A, which you already know because you solve, you're given that. Forces at C, forces at E. For the back leg, you already know the reaction at B because you solved for it last week. The reaction at D and at E. And then for the seat, again, at C and at D, which you probably have already solved for, but you should solve all 3 to make sure you got it correct. And W, of course, which you've done. So if you didn't do this last week or you want to do it again, you can solve for A again and reaction at B. That's what I did just to double check that I had it right. So that's this problem. There are a few things that I really want to point out in this problem that will make life easier. Let me first share to a different screen. So there were 2 things in this chair problem that I really wanted to help you out with to kind of hint and get you going along the right way. First thing I want you to do that will help is probably solve for the forces in the seat first. This is W, which I believe was 104.75 pounds. It's in the lab if you don't know. And then we're going to solve for, if I draw them this way and we go, oh, what point is that? This is going to be CX and CY. And then over here, we're going to have dx and dy. So you can solve for this first problem. It's a 3/4 member. The easiest way to go about this is to just take a moment at one of these 2 points. And if you take a moment at one of these 2 points, and because it's horizontal, that CX goes right through point D, or DX is along the same line of action as CX, neither one of these contribute to the moment if you take a moment at either one of these points. So you can solve for CY and DY. What I want you to keep in mind is if, say, for instance, one of these, and I'm just going to guess, I have to remember, but let's say CY ends up being some negative number. And there'll be a great temptation to say, oh, well, I got this wrong. The way that my free body ought to look is like this. And you'll go CY, CX, DX, and DY. Because you said, I know that this is negative. So I'm going to draw it the other way. Don't do that. Just let the number be negative. Come up here and say, this is a negative, whatever it is, 20 pounds, and leave it that way. Why do I say that? Because when you draw all of your other free body diagrams, when you went to draw, let's say, your front leg, RA, which I think was 84.5 pounds. Not that that's too important in what I'm trying to just talk about here. You had to have drawn the reaction here, CX, CY, and up here we had EX and EY. Now, when I went and put all my free body diagrams together into the one large free body diagram you had last week, you'll see that CY and CX are drawn in opposite directions so that when they're put together, their internal forces disappear. If you go and you do this because you've corrected for the negative, you'll need to fix your other free body diagram, because this is no longer a correct free body diagram if you've drawn it like this and decided the number is positive. Keep the number negative, and you won't have to do as much, I say fixing after you're done. What happens is people get confused and they draw this, but they don't fix this. And then they use a positive number here when it's really should be a negative number. So don't do that. That'll help solve any kind of problems you'll have in this. And I guarantee you that somebody's going to do that, but please don't. All right, quick little break here. Who can tell me where the deepest place on Earth is? It's in the ocean, of course, but where in the ocean is that place?
Marianas Trench in the Philippines.
Marianas, yeah.
Can anybody tell me how deep it is?
36,000 feet.
Wow, you're on it. Can you tell me when the first manned ascent took place into the Marianas Trench?
1950s. In the Trieste?
Trieste, yeah, it was a Bath Escape, 1960, very close. I thought I'd have everybody stumped. It was one of the things that got me into ocean engineering. I was sort of obsessed with that piece of history.
Which used gasoline for buoyancy.
I was going to point that out, that in order to get this thing to go, it was a Bath Escape, which they used lead weight shot to weigh it down, and they used gasoline for buoyancy. When they got to the bottom, they let go of the lead shot and it came up. And the reason they use gasoline is because it is incompressible, at least relative to air. So it doesn't crush. So the hull could only compress so much before the fluid started to take some of the forces instead of the air. All right. Wow, Jason, you blew me out of the water. All right. Let's go on to the second one here. I'm going to switch screens again. Well, let me share. We'll move down a little bit.
Do we have a value for A?
You solved for it last week.
So,
okay.
So it's the same.
If you're having problems with that, I did this problem, just to give you an idea, I did this problem starting from scratch, and I was very meticulous, and it took me about an hour, just to give you an idea. I assume it'll probably take you students longer. It almost always does. It's what I call student time. It's sort of like what we call diver time. Everybody thinks when divers go to work underwater that when they go to unscrew something that it would take as long as it takes for somebody to unscrew something on the surface, and it never does. It takes 2 or 3 times longer. So it's a similar kind of concept. When the instructor does it, it goes much faster than when the student does it, because you're doing it for the first time. So here's the jack, and this is again a very simplified view. If you look at my jack, you'll see that they actually have little gears in there, and the gears are there primarily to aid this thing in going up and down in a nice level way. In this case, though, what I want you to do is to find the forces in the top plate, link bar A and link bar B. The reason I don't care about those bars on the left-hand side is because this problem is symmetrical. So if you solve for A and B, also the thread rod, you'll see that the left and the right side are the same. What I want is the top plate, link bar A, link bar B, and the threaded rod. Let me give you a couple of clues on this one. I'm going to stop sharing for a second. And I'm going to go back to the other camera. We'll look at our jack again. So if we look at this jack, this would be the top plate. This is A, link B, and a threaded rod. And the way this threaded rod works is that there's a little thrust bearing in there, but this is a big pin that it goes through, so there's no moments being translated. Same on the other side. The trick to this problem, first of all, is to start with the top plate. This is a 3/4 member because we have a load right in the middle, and then we have 2 pins. So we're going to have a 3/4 member right here. And then we have 2/4 members. This is a 2/4 member. There's only going to be from this pin to this pin. And then this is also a 2/4 member from here to here. And then this threaded rod is also a 2/4 member right here. So let me come back and draw just a little bit. So Jason, how did you know that stuff?
I worked at Hui.
Ah, that explains it.
So
And who isn't curious about the deepest point on Earth, anyways?
maybe this is just how I drew it last week. But when we did the chair last week, I had W between what we're now calling points C and point D. And now
Yeah.
it's
It shouldn't be, but it's okay if you drew it that way.
okay. And the value that I got for distance was 3.88 inches. Is that the difference? Is that the distance between W and C?
That's the difference between W and A.
W and A. Okay, cool.
Let me double
So
check.
I just drew it weird. I just drew it weird last week.
Yeah. Double checking that that is indeed correct. I had 3.53 inches. I just I'll put it up here in the corner here.
That's for that distance A is the 3.5.
Yeah,
Okay.
that's what I had. So when we're looking at this, and I draw 3 body diagrams here, this top bar, that was F, right? And there's a temptation to, and there's nothing wrong with this, but I'll explain what's going on. We could do this as, let's arbitrarily call this A and B. Actually, let's call this E. Well, we have AX, AY, and we'll have E, Y, and EX. So we could draw it like this, and we could certainly solve for each of these right now, but this isn't really what's going on here. We know that AX and EX are probably not going to be 0, even though it shows that might be your inclination. But let's look at this other member here. Let's look at link A. And we know it's a 2/4 member. So we know that we're going to have a force A and a force A, like that. They're going to be equal and opposite. And so that's the way it's going to end up getting drawn. So really, this 3 body diagram here, and it's the same on the other side. We would draw this 3 body diagram, F, and that equals 4,000 newtons. A, E. Do it this way. We happen to know this angle. It's given in the problem, 45 degrees. So we can break these into components if we want to solve for the moment But this is what makes this problem doable. Otherwise, we'd have a gazillion unknowns. So when you're doing your table of forces and magnitudes and directions, do it as one force on this. So that's the first trick. This is a two-force member problem in the sense that link A, link B, and the threaded rod are all two-force members. The other trick, I'm going to go back to looking at my scissor jack. When you're solving for, like I said, now we've got force A going along here, force A going along here, and we've got force A. And so if we say, oh, well, how am I going to solve for this? Especially when we get down here, each of these things by themselves is, well, how do we know? What we're going to do is we're going to solve for a free body diagram of the pin, just the pin. Let me come back and this way. So if I draw the pin, big circle, I now draw my free body diagram of the pin. I'm going to have force A equal opposite to that spot. And I'm going to have a similar thing down here, and that's link B. We're going to call that force B. And then we're going to have a force from the threaded rod, T. Again, this is all because we have two force members right here. So now this becomes quite doable. We can solve because we're going to find out A from here, work our way down, put an A in here. We're going to know that the vertical component of A has to equal the vertical component of B, and then we'll be able to know the magnitude of A, and then we'll be able to solve for A and B, and then we can solve for T. We of course again know these angles. It's the same angle up there, and because it's a scissors jack, the angle is the same up and down. So that's the trick on how to solve these. Hopefully with that information, you'll be able to do this fairly straightforward. I always say that with great expectations and hope. Of course, you have problems. That's why we're here. I've given a fair amount of time to do this. I think I gave it till 8 o'clock tonight. Like I said, it took me an hour to do the first problem. I think the chair is probably the harder problem. Once you understand what to do with the scissors jack, it is significantly quick and easy. But the important part of the scissors jack is understanding those points that I just gave you on how to solve that problem. If you try and solve it without doing the free body diagram of the pin, you will be infinitely lost. Just as a point of future reference, this scissors jack is sort of a prelude to what happens in trusses, which is, I think, 2 weeks away. I think we're doing friction next. Anyways, so that's hopefully how you can solve those. Does anybody have any questions about that?
Can you swap back to the whiteboard drawing for my notes?
Absolutely. You just wanted to have a look at it?
Yep, great. Thanks, Scott.
Yeah. So I encourage you to draw all the free body diagrams for each of these. So for the chair problem, you should have at most, the most useful ones for the chair. Chair will have probably 4 free body diagrams. And one for each of the individual members, and the 4th one is for the overall, all of them combined, which is what you were working with last week, with the free body diagram you were working with last week. Here, and the reason I'll show you actually a quick way to check this at the very back. For your jack, you really are going to have You only need to use two. You really only need to use this one and this one. You only need to use two, but I'm going to encourage you to do free body diagram for the top plate, both arms and the threaded and the pin. That would be 5 free body diagrams. Again, you only need 2, but drawing all 5 will give you a sense. When you're presenting the solution to your problem, is it okay I erase this now? You guys good with this? I'm going to erase this and show you a great way to check on the chair that you got things right.
Hey, Rob. Rob?
Yeah.
I had a quick question about your distance for A. How did you get the 3.53? Because a few students and I keep getting 3.88.
It's possible I'm wrong. I'll double check my answer.
Okay, thank you.
So I have, well, let me put it up there.
Yes.
So this is for our seat. This is our seat. We have W. And I'm just going to deal with the vertical forces in this case. I'm only going to draw those. I drew CY and DY. All right. Oh, excuse me. I'm not in the right spot. That may be why I got it wrong. I would go with your answer at the moment. I believe I did it this way. I solved it here first, rather than the big free body diagram. Hold on, no, that's correct. I use a different free body diagram.
Someone in the chat said that you used a massive 84.5, and I think that's right because I used 84.5 and got the 3.53, but in the problem you wrote 82.5 for.
I will explain the difference. Use your numbers.
Okay.
So what numbers did you guys have?
3.88 for the distance of A.
Yeah, okay. All right, that explains it. I'll have to rework all my solutions, but methodology is correct, just the wrong number input. So you can see how you can easily get goofed up. Where was I going here? This wasn't the initial thing. It was, oh, how to check. If you draw all of your free body diagrams, and you actually put your numbers on there. W is 104. Let's see, I can do that. 104.75 and whatever this is, 20.75 and 30. I'm just making these up right now. When you put all these numbers together, you should see, you know, opposite direction, 20.75 going up on your solution for this one. And over here, you should see, you know, 30 down. And all those should add up. Well, again, all of your internal forces should disappear, just as what we talked about when you're drawing free body diagrams. So if you basically take all your free body diagrams and label all the forces with actual numbers and then look at that, that should give you a really good idea if you got the problem correct or not. Of course, all of my numbers are going to be incorrect because I started off with 84.5 pounds rather than 82. So I'm going to need to redo all of my numbers on my problem. But I'm going to send you guys into breakout rooms. So this, I'm curious. Some people have preferences about what rooms they go into, and you can put this into the chat box. I can let you guys choose your rooms, or I can assign automatically. What I don't want to have happening is people working alone. So, all right, I will try. Let's participants choose. If somebody ends up getting left alone, we can just put them in some rooms. So let's try that this time and see how that goes. I've got 7 different rooms. Hopefully that should give, so you guys get to choose, I believe it works. Let's see how this works. You guys choose your own rooms and away you go, I guess is how that works. So you guys need to sort of chat with each other and figure out what room you want to be in.
I'm not seeing, I don't know how to get into a breakout room. I just see the host has opened breakout rooms. Please wait to be assigned.
What happens if you click on that wait to be assigned thing?
Nothing happens.
Okay, somehow Daniel Leopold or David Leopold and Daniel Siegelberg managed to get into a room. Let me see if I can shove people. That's always possible. Marcine, where are you, Marcine? I don't see Marcine yet.
How, I understand. Are there different like rooms that I can see? Because I'm like getting invitations to rooms I'm not aware of.
Like I said, this is a trial for me. I can close all the rooms and just have them automatically assigned. That's certainly easier for me. This is a bit of a traffic cop situation, and I'm trying to figure it out. So that's probably what I'm going to do is I'm going to bring everybody back and just assign them, and then as people request, let me move them around. I think that's easier. So, experiment fail.
I didn't even know that Zoom had a pick your own breakout room option.
Somebody told me that it was a brand new function, and I have yet to figure out how it works. I saw it there as an option. So. All right, it's got to wait 30 seconds to close out, and then I'll automatically assign. And then, of course, just chat with me or come out into the main room and reassign you as required. But I think that's easier for me anyways. Seven seconds, everybody will be back in 4 seconds. 3, 2, 1, 0. Okay. All right, we're going to try again. So did you guys get an invitation?
Not yet.
Not yet.
Correct.
You can just basically choose the breakout room that you want by just going to like the toolbar where it says chat, share screen. It should show up.
It doesn't, Tony. It just doesn't.
Might depend on your version of Zoom.
Alrighty, I think I'll just start dumping people in rooms. So.
Did it just go back to the same rooms that were going on before?
At this point, I think you have the option to choose somehow if it's a option on the version of Zoom that you have.
Okay. So we just go into a room.
I still haven't been assigned a room.
Working on it, Maria. Like, me manually assigning it is far more cumbersome than.
All right, I'll be in room 2.
Okay. And as usual, Andrew, if you want to work the numbers 1 through 3, work your way down, that would be great. I'll work from the top down.
Okay, cool. I got to take a quick 5-minute break and then I'll hop in the room.
Okay.
Cool.
Hey, Rob, can I be moved to room 1, please?
That was Marcine?
Yeah.
Yep.
Hey Rob, can Tim and I get into room 7, please?
Okay. I'll put you in Tim's. Oh, I see where you are. Hold on.
Hey Rob, could we actually get permission to share our screen so we can draw on the diagrams that you have on Canvas?
Yeah.
I changed it. You guys should be good.
All right, cool. Thanks, Andrew.
Yeah.
All right. Go grab a cup of coffee and I'll be back.
What's up, Andrew? Hey, Rob. Sorry, I lost power. Could you throw me in a chat room? Sorry, I can't hear you. You're on mute.
It mutes me every time I come back. Where would you like to be?
It doesn't matter.
Do you remember who you were with last time?
No, I lost power like right before you sent me on break or the break room.
I'm going to send you to room 2 with Angel, Geraldo, and Laura. Is that okay?
All right. Yeah, that's fine.
Hi, Myra. You get kicked out or do you just leave?
No, my laptop turned off, so I got kicked out pretty much.
Do you want to go back to that room or you want to join another room or you want to stay
No,
here
that-
or what do you want to do?
Yeah, that one's fine. But before that, I have a quick question.
Yeah.
Let me see here for the part B. The forces on the rod, I'm a little confused since the A and B are linked at that point. So do we just choose a certain direction?
Yes. Let me switch to my video camera, my board.
Because there would be 3 on that at that point, right?
Yes, there will be 3 forces on that point, which is why I said take the free body diagram of the pin.
Oh, okay.
Make sure you work on the pin, because otherwise, when you just look at each of the bodies, you don't have enough information to solve. You know, if you're looking at just one of the bars. So when you look at that top bar, top plate, that's top plate. If we look at Lake A, I'm going to draw them opposite so that my internal forces cancel out. A, right? If I draw the pin, let's draw the pin. I'm going to draw, again, A opposite. And I'm going to draw T this way. That's the force on the thread rod. And then I'm going to have a link at B. And just for ducks, I'm going to draw the B here. That make sense?
So T would be pretty
So if I
much,
had the threaded rod, if I drew the threaded rod, which would be right, I'm going to put it right there.
mhm. So we're solving for T and for the pin.
Yeah. So you'll solve for, when you're here, you know all the angles of all of this stuff.
Mm-hmm.
You'll solve for A by solving this one here. You know, it's halfway.
Yeah.
So you'll know the angle of this, you'll know the angle of this, you'll know the angle of that. Then it's just a matter of solving for this, and then T is this and T is that.
Okay.
So
Okay.
really,
Yeah, that makes sense.
you only need to do two free body diagrams. This one and this one.
Mm-hmm.
That's it.
Okay. Okay. Thank you very much.
Yep. And what room were you in before? You were with Daniel.
Yeah, Daniel and someone else. I forgot his name.
I got it.
Okay. Thank you.
All right. Are we free to leave, or
Oh yeah, you're definitely free to leave. You've been free to leave for a while. I've just been staying here to kind of help out people.
got it?
I want to make sure everybody has the tools to solve the problem.
Oh, actually,
Well, you're free to stay too, but I'm not going to be here.
I do have a question about the free body diagrams and figuring out the direction of the reactions. And so I just get confused when we figure that. So when we're looking at the entire sketch, hold on, let me refocus. When we're looking at the entire sketch, how exactly do we know which direction our reactions are going to go in?
Ahead of time, we don't.
Okay.
We just make sure that when we draw the free body diagrams together, that the internal forces cancel out.
Oh, okay. So
that's the most important thing to do.
Okay, so when we break them apart, we don't really know exactly which way the reactions are going
until we solve for it. Yep.
Okay, thanks. All right, that's about it.
So I just wanted to let everybody know I'm not going to be here. I'm going to check out. Andrew is in his room if you want to join him. Or you can stay here. It's also fine with me, but I'm not going to be available anymore. So it's up to you.
Hello. Hi. What happened? Oh.
What was that, Gerardo?
Nothing.
Okay. So I'm
Thank
going to mute myself and stop videoing. Like I said, you're free to stay. I can put you all back in your rooms. Whatever you want.
Yeah, if you can make that available, I'll take that.
Okay. So I'm going to open all the rooms, and then, like I said, I'm checking out, but you guys can stay.
Thank you.